Good evening, everyone. And welcome to the Denver Museum of Nature and Science. I'm Steve Lee, one of the space sciences curators here at the museum, and it's just a thrill to see all of you here tonight, and it's going to be an amazing thing to see the people that you'll be hearing from tonight. So you'll meet them in just a minute, but we wanted to start with a very brief video that actually includes 3 of the folks that'll be on our panel tonight.
There's a mysterious zone far out in our solar system. It's a region of ice worlds, some solitary, some with moons. Their names may be unfamiliar. Eris, Makemake, Haumea, but they hold clues to all our origins. And the first of these worlds, and the one we'll reach in 2015, is the king of the Kuiper Belt, Pluto. The long journey of NASA's New Horizons mission began in 2006 aboard America's biggest, baddest rocket, tricked out with every conceivable booster.
We built a very light spacecraft and bought a very large launch vehicle, and the combination is ferocious.
But in some sense, it all began in 1930 with Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, but willing to spend long hours scanning star fields to find a moving point of light. Humanity's first glimpse of Pluto. The dream of actually getting to Pluto began with a 6-year-old boy in love with science, who grew up to lead a team of brilliant researchers and engineers with dogged persistence through decades of planning and building and testing. A race against time just to get to the launch pad.
Exploring the outer solar system, because it's so far, takes a lot of time. It requires a lot of patience, a lot of dedication, a lot of perseverance, but it's the frontier.
Assuming all goes well at Pluto, NASA may choose to extend the adventure further out into the Kuiper Belt, the solar system's mysterious third zone.
This is maybe the one chance in my lifetime that we're going to get a spacecraft out there and look up close at one of these Kuiper Belt objects.
December 6, 2014. New Horizons wakes up for the last time from hibernation.
New Horizons is speeding towards Pluto at a phenomenal rate, and we can't wait for it to get there.
January 27, 2015, 6 months of approach science begins. July 14, 2015, New Horizons' long journey, 3 billion miles, 9 years in flight, and 85 years of speculation about Pluto, climaxes in one day of close approach and flyby.
You know, we're rounding third base and we're headed home.
The dream, the adventure, the promise of discovery. That's what makes 2015 the year of Pluto.
So that's why we're here tonight, is we're on the verge of this new frontier. So our first speaker is Alan Stern. Alan is the principal investigator, that is the lead scientist, the lead person on the New Horizons mission. Alan is Alan's a graduate of CU Boulder, and he's a veteran of over 24 missions into outer space. He's currently also the vice president at Southwest Research Institute up in Boulder. And as you'll hear, he's been pushing for a mission to Pluto since the late 1980s. And Alan, your mission is almost there. So we're really looking forward to this happening and having you tell us about your journey to Pluto. Our next speaker is Fran Bagenal. She's a co-investigator on New Horizons. And Fran is also a veteran of numerous missions to the outer solar system, including the Galileo mission to Jupiter, the Juno mission, which is en route to Jupiter, and starting way back when, the Voyager missions, which were the first spacecraft to actually fly beyond the into the outer solar system. And like Alan, she's been a strong proponent for decades of sending a spacecraft to Pluto. And so she's looking forward for her own research of seeing how the solar wind interacts with this most distant of objects in the solar system. And if we talk to you about 2 months from now, I expect you're going to have some amazing things to tell us, as well as everyone else on this mission. The next speaker is Jamey Szalay. Jamey is the lead graduate student on the... He's the lead student on the Venetia Bernie Student Dust Counter, which is built and operated by the Lab for Atmospheric and Space Physics up at CU Boulder. And this is the only student-built instrument ever to fly into deep space from NASA or any country. So Jamey, being the youngest person that we have here tonight, he's going to give us a little bit of insight about the special connection that Pluto has for younger people. And by younger people, I think, speaking for myself, I'm an older people that grew up when Pluto was a Disney character as well as a planet. And so you can distinguish the younger generation's view of how Pluto came to be one of the more famous objects in the solar system. And finally, we have Joe Peterson. Joe is the New Horizons Joe is the New Horizons data downlink lead, which means he's getting busier and busier every day as the data coming back from the spacecraft turned from just a trickle early this year to, I guess eventually we might call it a fire hose. So Joel will be one of the people that will be making sure that all that data get back and get into the hands of the scientists and engineers that are waiting to use it. In his copious free time, when he isn't minding to New Horizons mission, he's also a great lover of the outdoors, including mountain climbing and parachute jumping. So maybe we'll have some slides of that. But he's going to tell us how New Horizons manages risks over the course of the mission and why being part of a team is the only way that a mission like this can actually happen. So in just a minute, we'll actually hear from these folks, but I wanted to just do a couple of customer service or public service announcements here. We have a few websites. This is a really fun one. It's called Pluto Time, and we'll come back to this, I think, at the end so you can see the web link, or maybe Toby, you can turn the light down because it's really shining on the screen here. This Pluto Time website you can put in wherever you are on the Earth, and it will tell you what time of day to go out and be outside when the amount of sunlight you're getting is the same as what we're getting on Pluto. And I think you'll find that a very interesting activity to do because there's not a whole lot of sunlight as far away as Pluto is. And what they're encouraging you to do is go out and take a selfie and post it on this website. And so we'll have the view under Pluto illumination from all over the Earth. And I think our final just advisory is at the end of our presentations, we'll have plenty of time for questions and answers. And afterwards, we'll also have a chance to go out of the theater down back into the lobby where you checked in and mingle with our panel for a while. So at this point, I'll turn it over to Mr. Pluto. Alan, take it away.
Okay. Thank you, Steve, and thank you all for coming out tonight. You know, the United States has been first to every planet in the solar system. It's something we're going down in history for, and it's been a long time since we've done anything like this, since the late 1980s with the Voyager program. For the kids in the audience and for many of the younger people, you probably weren't born during Voyager or you can't remember it. In fact, according to the Census Bureau, about half the people in the United States have never seen anything like this happen before. A point of light becoming a planet before our very eyes in just a matter of weeks. But that's what all of you are going to get to see next month, thanks to New Horizons and this wonderful team of people represented by the four of us. Over 2,500 Americans worked to build and launch New Horizons, many of them in Colorado. It's not just a team of individuals, but it's also a team of companies and organizations, universities, that all played a big role in this. And in fact, I want to recognize a few people and a few companies that I know are here tonight. I'm going to start with United Launch Alliance, who builds and flies the rocket, the Atlas V, that we fly on. Vice President Chris Chavez is here. Please give him a round of applause. New Horizons wouldn't have gotten anywhere if we couldn't have gotten off the launch pad. And of course, ULA gets the lion's share of the credit for that. Our main remote sensing suite, the main set of cameras and composition spectrometers on board, was built by another Colorado company, and that's Ball Aerospace. Linda Hardaway is here, and I think Bob Parizek. Lisa, if you could stand up. And Bob, if you're here. Bob was our project manager, and Lisa was the deputy on that. And we sure appreciate everything Ball did to get us going. And the University of Colorado was involved, small companies like Custom Microwave, and Lockheed Martin themselves, and there are more. There are individuals in Colorado also who played a big role. Let's see. Is Carol Stern, is my wife here? Let's start with that. Where's Carol? Please stand up. But just wait. I understand Jamey's mom, Linda Szalay, is here. And Linda, if you could also stand up, right? And Joanne Pietersen, Joe's wife. Where's Joanne? There you go. So, it's people, it's our families that put up with us being on airplanes year after year to make this kind of thing happen. And I just would appreciate if you'd give a round of applause for them. They're the unsung heroes of New Horizons. So we're going to have a chance to tell you a little about this mission tonight. And looking forward to doing that and then answering your questions. And by the way, I don't want to forget this. New Horizons has the coolest bumper sticker in the space business. It says, if you're not in the front row, my other vehicle's on its way to Pluto. And for the first few of you that ask questions at the end, Steve's going to give you a bumper sticker. So don't be shy. Think of your questions now. Okay, let's see what slides got put together here. Oh, we're going to start with a little bit of a story about the Kuiper Belt, the third zone of the solar system, the largest structure in our planetary system, where Pluto orbits. Beyond the orbits of the giant planets is this region that actually is larger than all of the space from the sun all the way out to Neptune by a factor of several. The Kuiper Belt contains billions of ancient comets, hundreds of thousands of planetesimals, the building blocks of the planets, and a handful of small planets, of which Pluto is the brightest, the first discovered, the largest, and to our knowledge, the most complex. These are the planets of the Kuiper Belt. They're shown here to actual scale, and you can see Pluto there next to Eris, almost its twin. They're shown with their actual colors, with satellites in the correct number, to our knowledge, when they have satellites. And you see there's a lot of diversity in this population. Smaller and bigger objects, some are red, some are blue. Some are covered in ices like nitrogen, carbon monoxide, methane, others in water ice. Some, like Pluto, have an atmosphere and seasons. Some have mini-moons, like Pluto, already 5 that we know about. Others have no moons, and some just have 1 or 2. Almost no one predicted this. We didn't know that the structure really existed until the 1990s when it was first discovered. It gave us context for Pluto, and the biggest surprise of all is that the solar system has more planets than we expected. So let's have a show of hands. How many people would say that our solar system has 8 planets? Some. How about 9? How about the real answer? It's not 9. The real answer, coming into view now, is there are hundreds of planets. But don't worry, you will not have to memorize their names. Any more than we make you know the names of all the stars or all the rivers of the earth. But it's so 20th century to think of the solar system as 8 or 9 planets. These are the planets of our solar system. Every one of these objects is real and have been discovered, mostly in recent years, by the very high technology telescopes and detectors that we now have to do Earth-based astronomy. This is a more accurate census of our solar system than anything that we had before. And as I said, Pluto is the first discovered, the harbinger of this entire population, the largest, the brightest, the most complex, and the one that New Horizons is about to explore. This is the spacecraft. Oh, a little too fast there. That's New Horizons. We built the smallest spacecraft we could get away with. Then we bought the biggest rocket that anybody would sell us. We basically launched a big tricked out Atlas V empty. Somebody called New Horizons the hood ornament on top of that Atlas. And that combination was ferocious. This spacecraft is all wrapped up like a thermos bottle. That's what all that gold foil is. It's thermal blanket. The dish is the communications antenna. The black hair curler looking affair is not a hair curler, but you probably knew that. It's called an RTG, It stands for radioisotope thermoelectric generator. It's a nuclear power supply so that we can go far away from the sun where solar arrays don't work because the sunlight is too faint. And we use nuclear power to generate heat and electricity aboard the spacecraft. Like I said, it's called an RTG. Without it, we couldn't do this mission, so I redubbed it. I call it the really terrific generator. It makes these missions possible. So this spacecraft has everything we need in it for the entire journey and for the exploration. On board, guidance systems, main computers, command and data handling, communications, propulsion, fuel tank, 7 scientific instruments, solid-state memories to put the data on board, and all the other subsystems that we need. And just like Noah's Ark, there's 2 of everything on board so that we have a backup when something fails. Fortunately, 9.5 years in flight, and we're not using any of our backups. New Horizons is working perfectly. It's full of fuel. Thank you very much. It's a credit to the engineers who designed it and the technicians who built it and tested it thoroughly that this spacecraft has performed flawlessly. On board that spacecraft are 7 scientific instruments that together represent the most powerful battery of scientific instruments ever brought to bear on a first reconnaissance mission. They dwarf the capability of Voyager because they come from 2000s era, 21st century technology. Let me give you a couple of metrics. Those 7 instruments combined are miniaturized. They're so miniaturized that all 7 together weigh less than just the camera on the Cassini Saturn orbiter. All 7, turn them all on at once, all of their microprocessors, all 7 draw a combined total, fasten your seatbelts, they draw 28 watts combined. That's a night light. And yet they carry tremendous capability. Our infrared composition mapping spectrometer has 64,000 pixels. The equivalent instrument on Voyager had precisely 1 pixel. On Voyager, the ultraviolet spectrometer had 2 pixels, better than the infrared. The ultraviolet instrument on this spacecraft carries 32,000 pixels. The capability that we're bringing, 9 cameras, 2 spectrometers, 2 plasma instruments, 2 radio science instruments, and Jamey's student-built dust impact counter are just an amazing capability. We're going to give you maps, color maps, composition maps, topography maps reconstructed in 3D, thermal maps. We're going to give you the composition of the atmosphere, the escape rate of the atmosphere, the temperature pressure profile, and more. It's just going to write the book. Forget rewriting the textbook. We're going to write it from scratch at Pluto. And here's Pluto. This is the best picture ever made by the biggest, baddest gun we have in astronomy, the Hubble Space Telescope. But Pluto's 3 billion miles away. So what can you tell when you look at that picture? I led the team that took that picture with the Hubble, and you, like me, could overinterpret it for science. Maybe that's a northern polar cap. Maybe it's not. We weren't sure back in the 90s when we took this picture. But if you look at it, you can't tell very much. Take a look at this. What is that? That's the Earth at the same resolution, the same pixelation as Pluto. What could you tell about this planet at that resolution? You can't even tell there are continents and oceans. And that's the situation that we have with Pluto until New Horizons. Our knowledge is going to go from a point of light to a real planet and more. Let me test you on this one more way to show you how poorly you can misinterpret. Take a guess. What are we looking at? Probably not what you guessed, right? At the same resolution, the American flag just as well be the planet Mars. And yet with New Horizons, we're going to bring the long eyes of our long-range reconnaissance imager to bear. That instrument will take pictures of Pluto as good as that picture of the Earth by the middle of July, and the very best pictures of Pluto that we will take will be equivalent to that picture in the inset of Manhattan and New York City. Can you see Manhattan between the Hudson and the East River? If you look carefully in the middle of Manhattan, you can pick out Central Park. If you look really carefully, you can see the ponds in Central Park. You can see the wharfs on the Hudson, and you can see the main thoroughfares of Manhattan running north and south along the island. Now, I have to tell you, if we discover any of that on Pluto, I have to get NASA permission before I can tell you. But that's the kind of firepower that we're bringing to bear. And so with that, I'm now going to turn this over to Fran, who's going to tell you a little bit more about what we're about to do. Fran?
Great. So I wanted to do some history. We're going to go back a bit in time and think about the earlier days. These are the earlier days of the mission when Alan there, young Alan in the glasses, got a group of us together to begin to think about how to go to Pluto. This is 1991, and we had been working already for a couple of years on thinking about why we would want to go to Pluto, how we could make the case to persuade the US taxpayers, people like you, to pay for us to go to Pluto. But it all started a long time earlier. In Kansas, a young man was keen to find a way to go to college. He was also a keen astronomer. His uncle had shown him how to build a telescope. And this is the most really cool picture, because this thing on the right here was actually a telescope that was made using pieces of farm machinery. That's actually a creamer piece on the right that he put together to make the telescope. So he used his expertise of knowing how to look at the night sky to get himself a job at the Lowell Observatory in Flagstaff, Arizona. And he went there to look at night using a telescope, but at the end of the telescope, he would put these plates, and on the picture on the right, on the left, he's holding these glass plates that are covered in a kind of chemical that when you put it behind the telescope so the light illuminates it, it processes the chemicals. And then the next day, he would go and process the plates and look at them with a very special machine called a blink comparator. And the next slide shows you what this looks like when you take two pictures, one after the other, a few hours apart, and you begin to see, you register it so the stars don't move, you get to see what moves relative to the stars. So you're looking for an object that is closer to us and moves a little bit relative to the stars. Can you see it? Can you see it? Can you see it? Can you see it? Okay, we'll help you. There and there, okay? It's really hard, isn't it? Okay, so he was really good. He was able to look, and he was able to find this object. And of course, it was sensational, because if it moved relative to the stars, it has to be closer, and so it's a planet, okay? It was orbiting around the Earth. Orbiting around the Earth, orbiting around the sun. This is post-Copernican revolution, okay? But it was a big deal, and it hit the headlines. So this was back in 1930, but since then, Pluto, on its 248-year orbit around the sun, has not even gone halfway round, okay? It's so far out there that it takes a long time to orbit the sun. Now notice over on the right, it says there, Discovery of Sharon, 1978. And the next picture shows you this discovery picture. This chap, Jim Christie here, was observing, and again, he used this sort of photography where you have a piece of glass or a piece of film by then, and you process it to try and work out what's going on. It's a very fuzzy picture because you have to look through the atmosphere, and that faraway planet looks really small. So Pluto here on the left is just Pluto. But on the right, you'll see there's a bit of a lump on the side. What is that lump on the side? What could it possibly be? Well, he looked and observed, took many pictures, and he saw that if this is Pluto, there appeared to be something moving in front and behind. And this was the moon Sharon. And it's a really big moon. It's about half the size of Pluto. So it's almost like a double planet system, and they appear to be moving almost around each other. So that was 1978. Now let's move on and look at modern technology using digital technology. So the cameras you've got in your phone works like this. You have an electronic detector, and once we started to put electronic detectors behind the telescope, we could do all sorts of things very quickly, because then we could take digital pictures, process them on computers. And now in 1992, we detected the second Kuiper Belt object after Pluto. And then since then, many, many more. And the next, I want to show you this film of the discovery, this computer simulation rather, of the discovery of these many, now thousands of objects. And so you can see, this is put together by Alex Park. It's a really clever simulation showing how we actually discovered these objects. They're moving, of course, orbiting the sun. The biggest one, of course, is Pluto. And then there are other ones, some quite big, some really small. And you can see that they're all over the place. Notice there's a gap just to the right of Pluto and another gap up at the top. We can come back to talk about that if you like later in the evening. But then if you now tilt it on its side and look at the plane of the planets, you see that they're scattered. Not all in the same plane as the planets. They're at different inclinations from that plane. So we need to now take a little bit of a time out to talk about the Kuiper Belt and how do we make a solar system and how do we make a Kuiper Belt? Why do we really care about the Kuiper Belt? Why is it important? And it is all to do with the formation of our solar system. How do we get from clouds up in the sky that we see not in the Earth's sky but out in the distant universe? We see clouds which we later know will form solar systems. We see solar system formation out as they're being formed out in the universe, and then we see our solar system. The question is, how do we get from there to there? Okay, so what we have is a big cloud. It begins to spin up, it begins to collapse, it begins to flatten out. We have a star at the center, which slowly begins to cool, and the disk begins to cool, and the objects move, they orbit the star. And as they orbit the star in a plane, they tend to accrete and accumulate. These are the small planetesimals that then accrete to form planets. And over time, they form these series of planets. But there's a problem with this. Let's look at the next slide that shows us that we have a problem. So if we take, yes, that's it. If you think about the collapse, you have the collapse spinning up, cooling down, and then as this disk cools down, the stuff that's close to the sun will be the rocks and the metals that condense at high temperatures. Now, there's not a lot of rocks and metals in the sun and in the universe, and so you form small, rocky planets in the inner part of the solar system. Now, if you move out, it gets colder. And as you know, as we felt this winter, it gets colder and the rain turns to ice. And the outermost part beyond the frost line, the ice condenses out, and you have these big icy lumps that are formed. Now, there's a lot of water, a lot of ices. There's a high abundance of material that forms ices. And so we make these huge snowballs that are around 20 times the mass of the Earth, that pulls in hydrogen. Hydrogen, the most abundant element in the universe, to make big, giant outer planets. Jupiter, Saturn, Uranus, Neptune. So this is a great story, but we have a problem. You can't make Uranus and Neptune in the age of the solar system where they are in the outer solar system. That's one problem. Another problem is, how do we make the Kuiper Belt? We have all these objects scattered in the outermost part of the solar system. So some clever planetary scientists used their computers to simulate what would happen if you took Jupiter, Saturn, Uranus, and Neptune, put them close in the solar system, where Jupiter is now, and then you put in all these planetesimals in the outermost part of the solar system, and let the gravity go. And what you saw was it went kapow. The orbital resonances between Jupiter, Saturn, Uranus, and Neptune caused this scattering, sending the Uranus and Neptune out, actually switching locations of Uranus and Neptune, and scattering the Kuiper Belt objects out to make the Kuiper Belt, these planetesimals forming the Kuiper Belt, but then also sending in water and material from those scattered planetesimals to the Earth and the Moon, forming the big impact craters that we see left on the Moon. Okay, so this was very useful for explaining the outer solar system. And here we have Pluto. And this picture is made by taking all of the information we have about Pluto, not just images from Hubble Space Telescope, but also all sorts of other information that we can take. And this is the best we can do. Okay, now can you see impact craters? Mountains? Rivers? Maybe, yeah? Oceans? Frozen lakes? Cities? Alien beings? Yeah, not a whole lot, right? Dark bits, light bits, red bits, not much. And that's the best we can do from Earth. And New Horizons is just about to reveal what it really looks like. Ta-da! So this is the view we have of the surface. If we think about what it really is in size, we have here to scale the Earth, Pluto and its moon Charon. Charon is actually not is more gray. And you can see they're about the right distance apart, about the diameter of the Earth. So these are substantial bodies, but much smaller than the Earth. We also know that Pluto has an atmosphere, a substantial atmosphere. It's also nitrogen, like the air that we're breathing in this room. And then we know that because of the weaker gravity of Pluto, that atmosphere escapes and leaves the planet Pluto and fills out a large volume. We think it may even fill out a volume that's comparable in size to that of the Earth. So if we then look at how this works, we then get, sorry, let me just say that we're going to measure that atmosphere, and we're going to measure that atmosphere by the New Horizons spacecraft is going to go behind Pluto, and as it goes into the shadow, we'll see the sunlight turning out. We'll measure that with our instruments to measure the distribution of gases around Pluto. Now, let's think about the environment in which Pluto is sitting. And this fabulous series of movies from the Solar Dynamics Explorer shows what's going on the sun. The sun is ejecting vast quantities of gases. These gases are very hot, and they are ionized. So we have ionized hydrogen, protons, and electrons forming the solar wind that streams out away from the sun. And eventually it moves out beyond the orbit of the Earth, beyond the orbit of Mars, Jupiter, Saturn, Uranus, Neptune, and of course out beyond Pluto. And the Voyager spacecraft has been going out to the very edges of where the solar wind interacts with the interplanetary medium at 120 times the distance between the Earth and the Sun. So that's 4 times further away than Pluto. So what happens when this solar wind comes in and hits the escaping atmosphere of Pluto? We think it forms this big volume of interaction region around the system. But the truth be told, it's total guesswork. Okay, so we have a better idea of what the surface might be like if we use Voyager 2 as an example. Voyager 2 in 1989, I was on the Voyager mission. It's great fun to see for the first time this moon. It's a captured moon of Neptune. It's in a retrograde orbit, and what it looks like. So look at this and look at the geology. What do you see? You see some cracks. Maybe you see some craters. You see some black things. You see some ice. Let's look at the movie that goes in. It's a somewhat of a simulation, but you can see these impact craters. You can see cracks. You see pieces of ice. You see sort of frozen lakes. And then you also see this black stuff. Black, big chimneys of black material that come up, and then the winds carry them sideways. We don't really know what the black stuff is. It's probably some really carbonaceous material, very primitive organic material. It probably isn't bugs. It's probably more like, very simple chemicals. But we don't really know what it is. Will we see this on Pluto? We have no idea. It's going to be interesting to see. So remind you, this is our current view, our best view, really, that we have put together, synthesized, of Pluto. And as New Horizons is on its way and getting there, we're beginning to see more. So check the website, because every day there's a new picture, or nearly every day there's a new picture. So what is it like inside? We know it has an atmosphere. We know that frost condenses out to the surface in places. We know that there's methane and nitrogen ice. There's probably water ice. We think that it's about half ice, half rock from the density. And so we don't know what it's really like inside, but we suspect that we'll have this thick layer of ice outside. The question is there a layer of water under that ice? I mean, Pluto is really cold. It's at about minus 370 Fahrenheit. It actually doesn't matter whether you use Fahrenheit, Celsius, or Kelvin, it's bloody cold. But is there inside enough warmth generated inside to make a liquid layer? We don't know. Could be, but it is just guesswork. Okay, so time to go and have a look. Let's have a mission. So back in 1989, the US Postal Service, or around then, put out a bunch of stamps, and it showed all the planets of the solar system, and then Pluto not yet explored. You can guess the date by the cost of the stamp. 29 cents for a stamp. Long time ago, okay? And you can also tell it's a long time by looking at Alan and me. Okay, so we started working on a mission. Eventually, after a period of time, we actually wrote a proposal to NASA several times. We tried to get things going, but here we are, 2001. The team for New Horizons put together a proposal. We asked NASA, could we do this? They accepted. We started building it, and we'll have a picture here of the spacecraft. Alan showed you this before. RTG is the bit sticking out, the generator. 2005, we tested it. You have to shake, and you have to bake it, and you have to wiggle it about to test that it will survive in space. And then finally, in January 2006, we have the launch. And here we are.
Of ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. Plus 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
Whoosh! Up it goes into space. Fantastic. Just as fast as we got. Big relief. Oh, thank goodness, we got it in space. But this is really rather bizarre. So we thought we were going to go and explore Pluto and Charon, right? It's almost like double system, a Pluto and a big moon. Just a few weeks before we launch, we find, uh-oh, Hubble Space Telescope, we see 2 more moons, Nix and Hydra, okay? And since then, we found another 2. There are 5 moons. So thing has just got a lot more exciting on the way there. We didn't plan this, we didn't propose this. It came along. And who knows, there could be another 5 more out there. We don't know. We'll see as we get closer. And so we're going to fly through this, sorry, could you go back? Yeah, we're going to fly through this system. And what we have, in fact, is a system, it's almost like a bullseye with the moons going around. We're going to fly through it with the New Horizons spacecraft and take pictures as we fly through the system and send the pictures back to Earth. And we're going to hear a bit more about this from Joe in a bit. But what's interesting is we fly through this whole system, right? So I'm at the New Horizons spacecraft, and there's Pluto, and we're going click, 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 and then send all the information back to Earth with the antenna, right? How long does this flyby of the close part take? 2 hours. 9.5 years for 2 hours. But spacecraft's working well, everything's good, and you'll hear all about what's involved in making it happen. Because indeed, it's very complicated. We've got to take pictures of 5 different objects. You're not going to be able to follow this, but the point is, over this short period of time, we have to plan exactly how the camera will turn and look and of these different things and make different kinds of measurements with all those different instruments, and then eventually we'll send the data back. But what's interesting is we have to plan and arrange all of these sequences. We don't have the communication time to just do it real time. We have to put all of the plans on board. Spacecraft has to execute them and then send the data back. So this is the operations team. They're putting together the plans. They're deciding what to do and how to make it work. And you'll notice something very interesting about this team. Back in the Voyager days, it was mostly blokes. It was all guys. There weren't very many of us women on the team. Now we have a lot of women on the team. Women engineers, women scientists, women operators. Many women are working on this project and doing a great job of planning and making it work. So we're going to be arriving in July 2015. We're going to take pictures. We're going to collect the data. All of the instruments are working well, and they'll do fabulous stuff when we get there. I can't wait to get there. But before we do, Jamey is going to tell you about what the best instrument, my favorite, is going to do when it goes by. Or it's doing already on its way. So tell us, take it away.
Thanks, Fran. So today I'm going to tell you about a very unique instrument. That's the Student Dust Counter. Not only has New Horizons been pioneering its way and it's going to explore the Kuiper Belt, but it's actually pioneered student involvement in an instrument, in a mission. It's the only mission to send a student-built and run instrument all the way to the outer solar system. So I am one of many before me. This is a team of about 30 students, not all shown here, that poured a lot of sweat and time into making this mission possible. And I'd also like to point out Mihai Hirani up on the top left. He's the brainchild of this and the PI of this instrument. So this was back in the day. Yeah, we can. This was many years ago. I was still in high school when this was taken. And next we have a recent image. So this is a reunion we had a couple months ago, and all the SDC students came back and we were able to meet. Some of us hadn't really met in a long time. And everyone that was involved in this has gone on to do excellent things and gone to the grad school of their choosing. And it's been a really rewarding experience for them. So here's our logo. This is a student instrument, so we had a student-made logo, if you can't tell. And this is kind of depicting what we're doing. We left Earth, we're going to Pluto and beyond, and we're catching dust. We don't actually have a butterfly net on there. That would be silly, but this is depicting what we're doing. We're getting hit by lots of things. So some people might ask, well, how are you hitting anything? I thought space was really empty. And it turns out that while space is empty, there's a lot of stuff out there. It might be spread out, but there is a lot of stuff. So you have all these Kuiper Belt objects that we discovered in the 90s, and with each object, it's constantly getting bombarded by lots of material. And so you can imagine, say you take a rock and you throw it into sand at the beach, and it does something like this, where it kicks up, and then it falls back down. Well, on the beach, gravity is really strong, it just falls down. But out in the Kuiper Belt, when you have something smash into a body, it doesn't fall back down. It can't hold on to it, and it goes right out into space. It's just spewing out into space. Not only that, but we keep finding more of these things. And every time you find another one, that's another source of material that's just spewing dust, particles, micrometeoroids, whatever you want to call it, out into space. And once it's out there, it turns out the physics makes it slowly spiral into the solar system. It takes about 1 million years. And so there is, like Saturn has a ring, our solar system actually has a dust disk all the way through, and that's what we're plunging through and measuring with SDC. So SDC is actually not the first instrument, dust instrument to fly. We've had a slew of other instruments, as you can see here. But what I'd like to point out is that the farthest one, Pioneer 10, went to 18 AU. So that's 18 astronomical units, and one of them is the distance between the Earth and the Sun. It went out 18 times, but New Horizons, as of October 2010, has broken that limit and continues to break that limit every single day with a student instrument, nonetheless. So here's a depiction of some of the dust detectors we've sent out into the solar system. You can see Jupiter, Saturn, Uranus. That's how you pronounce it now. And the purple line is Pioneer 10. And you can see that it went out to about 18 AU. And then New Horizons is just going much farther out into the solar system. Another thing, as Alan mentioned, we have the most advanced suite ever sent to a first encounter. And the detector before us could detect particles of about 3 microns. To give you a rough scale for that, if you were to pluck one of your hairs, you don't have to. That's about 50 microns. So this is about 1/10 of the width of your human hair. But SDC didn't stop there. It went to 100th the width of your human hair. Now, what are we measuring? What's the point? Why do we care about dust in the solar system? That's a pretty common question. It turns out, if you were to look out into space at any solar system, pretty much, you're not going to see all the planets moving around in this beautiful dance. What you're going to see is a bunch of dust glowing because the sun, whatever sun it is, shines on it, it re-emits, and it's going to crowd out any planet you're going to see. And so by us learning about our own playground, our little sandbox, our solar system, we're flying through understanding our solar system, understanding how the planets pull around that dust. And once we can do that, we can understand what all the other solar systems look like billions and billions of miles out in the solar system. So with our own playbox, we can understand many different solar systems. This, if you were an alien or someone looking very far away, this is what you would see. Something like one of these pictures. You wouldn't see the planets. So there's the actual instrument. And just to point it out, it is right here. It's this thing, not these. They look pretty similar. Those have to do with heating. But it's right here on the spacecraft. The spacecraft is actually moving this direction, so we're stuck right on the windshield. And we're flying through space at about 36,000 miles an hour. It's really, really fast, just smacking into anything we can. And to give you an impression of the size of this thing, this is the cover that we had to stick on it to protect it while we were putting it on the instrument. So it's about the size of a pizza box, roughly. And it's, well, this cover is red. The reason this is a red tag item, and that's a remove before flight. Maybe you guys have seen a keychain, or anyone that's familiar with aviation, you got to pull some things off the plane before you take off, otherwise you get in a lot of trouble. Same with this. If we left this on, we wouldn't really detect much. So this was our cover, but it gives you a rough sense of the scale. And not only that, if we were to imagine, just to give you a picture of how big these things are or how small, if you were to take this and make it the size of a football field, so imagine our detector is as big as a football field, the particles that Pioneer could detect were the size of a marble. But SDC didn't stop there. We went even farther, and we can detect a poppy seed dropped onto a football field. That's how advanced this instrument is, student-built. Now, why is it called Venetia Bernie Student Dust Count? I've been calling it SDC, but it's actually VBSDC. And that's another way that some young guns were able to be involved in Pluto. Venetia Bernie actually was 11 years old when she named Pluto after a god of the Roman underworld. So that's a neat fact. Now, how does this thing work? Here is one of the panels, and this is a schematic showing the cross-section if you were to look at it sideways. That vertical dimension is the width of the silver part, not this plastic part. I know they might all look the same from there. But it turns out this thing is about 28 microns thin in the middle. It's very thin. That's like half your hair. And the way it works is a dust particle hits it, and just like in space in a body, it creates a little crater, except here it creates a very tiny crater. And when it does, it pulls out a little piece of this metal, and that changes the charge distribution on this, and that's what we measure. Very, very tiny charge changes. We have to, since it's a very, very sensitive instrument and very, very thin. So, again, this is a student instrument. So students were involved all the way from the design of the software to the testing to the calibration and then to integrating. Students pretty much did everything they possibly could for this mission, even at the undergraduate level. And so on the next slide, not only that, but this is a NASA mission, and just because it's students doesn't mean you can slack off. They actually had to satisfy every single requirement that any other instrument had to satisfy, because this is a NASA instrument delivered to a NASA mission. Not only that, but we were the first to deliver before any of the other professional instruments.
Budget, too.
And on budget, that's right. So, part of the testing, we had to do an acoustic test. So when you take off, you saw that really magnificent launch. Well, that thing is pretty violent for all the instruments, and you need to make sure that everything you put on the spacecraft will survive. And so what we had to do was acoustic testing and make sure that when you shake this thing, it's really going to survive the mission. And I'd also like to point out, if you notice, everyone was wearing these bunny suits in there. This is a dust detector, but while it's on Earth, we actually don't want it to get dusty. And so everyone has to suit up and make sure it's very clean. So couldn't give a talk about SDC without talking about the data. Here's the data to date in the outer solar system. And I'd just like to point out, these are the densities we're measuring. So it's about 10 per kilometer cubed. And just to give you a point of reference, if you were to stand in Denver and you were to drill all the way down to sea level, and you were to carve out about a mile swath and pick that whole thing up, in that whole volume, we'd have about 10 dust particles. It's very, very sparse out there. But we're still able to detect it. We get about one hit every single day, but we're there for a lot of days. So you add all those up, and you can get some really neat science out of it. And one of the neat results is that you can actually figure out how much stuff is being spewed out of the Kuiper Belt. And it turns out that's about 6 tons every second. So if you've ever had to shovel dirt out of a truck, that's about 1 truckload of dirt every second that's falling into the sun and making up this really beautiful dust disk throughout our solar system. Now, the same principles that made all this dust fly into the solar system, well, just like the Kuiper Belt, Pluto, we keep finding these darn moons, and every single moon we find is another source. It's getting bombarded, it's kicking stuff up, and the more we find, the more there is a possibility that there is actually a dust disk around Pluto. And not only is that scientifically interesting, but it's a little nerve-wracking for the hazard guys, because this could potentially present a hazard, and it's something that everyone is actively paying attention to, and it looks right now very optimistic, and is probably no issue, but it's a very interesting scientific discovery if we were to find a ring around Pluto. And with that, I'll give it up to Joe.
All right, well, thanks, Jamey. Well, it's great to be here. And after 9 long years of waiting, it's especially great to be arriving at Pluto finally. So my team is called the Downlink Data Team. And Downlink Data is all about getting all the raw data back from the spacecraft 3 billion miles away and doing what we do with it on the ground. And there's a lot of stuff we do. We assemble it into images, we make data files for the scientists, we calibrate them, and we archive them. We even archive them for long term so that scientists more than 100 years or more can look at this in the future. So when I'm not doing all this stuff, I like to do one of my favorite things, which is skydiving. Anybody here ever made a jump? Wow, quite a few of you. It's fun, isn't it? Well, and I was asked recently, what does skydiving have in common with this mission? And I'm like, wow, that's a really interesting question. So we made a movie, and here it is, so check it out.
Hi, I'm Joe Peterson. I'm the Science Operations Downlink Lead for the New Horizons mission to Pluto. And I'm here to take part in one of my favorite hobbies, that's jumping out of airplanes. You might think that after the thrill of jumping out of airplanes, that getting back to behind a computer and doing basically geeky stuff for a space mission might be not as exciting, but it's not true at all. Working on this project has an immense amount of excitement. We're exploring space. It's pretty amazing. So one of the great things about skydiving is all the teamwork involved. With New Horizons, teamwork is so important. We have many, many people in this project, and unless they all work together as a team, this mission just can't come together. One of the things we do just for fun in skydiving are jumps that are a little out of the ordinary. We take a hula hoop and we actually take turns diving through the hoop. On New Horizons, there's a similar thing going on, that we need to thread the needle as we go by Pluto. We want to go by just where we want to be, and we want to be the right place to take the best observations. And we have a navigation team that is doing this needle threading that is so hard. It requires precision flying, and we're coming up on the culmination of all this effort, all this planning. Very soon, we're going to go by Pluto and get the actual goods of what this whole mission is wanting to do, is discover this amazing place that we haven't explored yet. Quite naturally, the public believes skydiving is incredibly risky, but those risks can be mitigated. Space exploration is a risky business. and there's a lot of time and a lot of heart and soul involved. New Horizons, we've got 7 different instruments all taking data of different parts of Pluto, the atmosphere, of the surface. All the timing is so critical and has to be choreographed so well, and that's one thing that our science team has been working on for years. So after a great skydive, you throw out your pilot chute, your canopy opens over your head, and everything gets quiet. You no longer have that wind noise, and now you're just floating, looking at the mountains and flying your parachute down, thinking, wow, what a great job we just did. In New Horizons, that's the same kind of feeling that I think we're all going to feel after we've passed by Pluto, taken our observations, seen them come down, at least seen a good number of them come down, and saying, wow, we really got some great pictures, some great data.
So, thanks. That was a really fun video to make, and I want to thank my fellow skydivers for wearing cameras on their heads and giving us some of that cool footage so we could get our point across. So, when Alan was up, he gave you a bit of a quiz, and I have a few questions for you as well. So, shout them out if you think you know. First one is, how are these two similar? Anybody have any idea? Fast. I hear the word fast. Absolutely. Not only just fast, but fastest is the key word here. The cheetah is the fastest animal on Earth. It can run 75 miles per hour. And New Horizons is the fastest spacecraft that's ever left the Earth, leaving at 36,000 miles per hour. That's even hard for me to imagine. Okay, so next question. Similar question, but how are these two similar to? And the answer is not that New Horizons can make phone calls. All right, so the answer we're looking, a lot of good answers I'm hearing. The answer we're looking for is the memory on board. They have about the same amount of memory. So 8 gigabytes, a lot of you probably have phones with 8 gigabytes of memory. And you know that it's not, you put a bunch of apps on it, a bunch of music, a bunch of pictures, it fills it up pretty quickly. So the key point here is that the New Horizons teams had to work really hard to be careful what we put in memory. Okay, last question, I promise you. So how long do you think it takes commands to get up to the spacecraft and then also come back, for data to come back down from the spacecraft? Any guesses?
5 hours.
I heard 5 hours, which is very close. It's 4.5 hours. So 4.5 hours one way means it's a 9-hour round trip. So if we were to send a command to the spacecraft, we'd have to wait 9 hours to see what happened. So controlling this spacecraft with a joystick is pretty much out of the question. So back to the data for a second. So the raw data we get from the spacecraft is not very usable at all. It's a bunch of packets of binary ones and zeros. The scientists can't use it. Nobody wants to deal with that. And that's the whole reason for what my team does, is we had to come up with a way to automatically produce data that's usable by the scientists from this kind of randomized collection of stuff that comes back. And we call that the science data pipeline. So it looks kind of complicated here, but I can explain just the basics of it. So on the left side, we have packets. These little pink boxes are packets. And we pull those multiple times a day from our Mission Operations Center in Maryland. And we put them in our database here in Boulder, Colorado. We pull them over the internet. And then what we want to do is go back and look in that database for all the packets that make up a particular image or data file we're trying to produce, and then put them together in the right order, produce that data file, and then calibrate the data. So we produce 2 files, one uncalibrated, one calibrated, then we put it into the archive, and that's what our pipeline does. So you might imagine that this took some testing, a lot of testing actually. So here's New Horizons before launch, of course. It's in a clean room, and how can you tell it's in a clean room? Bunny suits, yes. So the bunny suits are there, of course, because we want to keep New Horizons clean, and people are really dusty. Okay, so one of the instruments on New Horizons is called Laurie. We've talked about that one before. It's the high-resolution camera that we're going to get a lot of great data back from. And that was one of the first instruments I was able to test with the pipeline. And it was very exciting because we hadn't tested any real data on it yet. And Laurie team said, hey, we have some packets for you. I said, give them to me. We'll put them together. So I had the pipeline crunch on those packets, make the image, and then the image popped up on the screen. And it wasn't at all what I expected. I expected some blurry image from inside the, I didn't expect anything from space, but I expected a blurry image from inside the clean room, something like that. But no, it was an image, plain black background image with the word hi. I picked up the phone, I called the Laurie team, and I said, I'm not sure, but I think your instrument just said hi to me. Should I be concerned? Is it self-aware? What's going on here? And they said, no, that's just a test pattern we use. It's exactly what you want to see. I said, oh, good, that's what I see. So how do we collect this data? Well, as has been talked about before, there's a team that actually makes the plan. They plan everything ahead of time, all the maneuvers. And what you're looking at is a very sped up computer-generated animation of the Pluto encounter. And right now you can see depicting a scanning of Pluto, taking images of the various parts of the system. And as you see, we're getting closer to Pluto. So we're going to take the really high-resolution stuff. Now we go over to Sharon, take some of that, back to Pluto. And just as we pass by Pluto right now, we turn and look back toward the Earth and the Sun, right through Pluto's atmosphere. And as Fran said, we have special instruments that are going to collect the data from that and actually let scientists figure out what that atmosphere is made of. It's pretty cool. And of course, as we leave the Pluto system, we'll be capturing some more scans. So that's what the encounter looks like in fast motion. Okay, so this next one is a detail, and this shows you as you get really close, the high-resolution images, Pluto doesn't even fit. We have to take a slew of images in these stripes, kind of like the panorama function on your cell phone, your camera, where you actually have to stitch the images back together. And that's exactly what we're going to do to get the highest resolution image of Pluto back on Earth and put it back together. So speaking of these great images, Alan and the project really wanted to make this available to all of you. And we put up a site, and you can get to it. There's the address right there. So I encourage you to go to the site. It has relatively raw images, so you see the images just like we first see them, before we've done anything with them. And new images are coming down every day. Well, not every day, but a lot of days. And it takes about 2 days before you'll see the images that just have just come down. But we hope you go to this page, and you follow along with us as we encounter Pluto for the very first time. Well, thanks. And I'm going to turn it back to Alan for some final words.
Great. Well, that was great, Joe. And I want to tell you there are a lot of ways to follow New Horizons. You can watch NASA TV. You can watch television specials that are being made by, well, you wouldn't watch NHK in Japan, but you'd probably watch the Discover Channel. They're making a special for next month. So is Nova on PBS, and so is National Geographic's. Or you can go on your computer and just Google Pluto New Horizons, just those 3 words, and you'll find Twitter feeds, Facebook pages, Instagram, Tumblr blogs, all that and more. You'll find our website, you'll find the NASA website, you'll find NASA TV, you'll find pages like the one Joe showed you so you can watch new images as they come down in real time. There are lots of ways for you to get involved. I'm going to tell you a little bit about our encounter, but I'm going to start with our first encounter. On the way to Pluto, we flew by the planet Jupiter to get a gravity assist. And we also used that as a test flight to test all of our instruments, our software, and our spacecraft, and to learn about the Jupiter system. New Horizons was the 8th spacecraft to visit Jupiter. And we made the cover of the Rolling Stone. Science magazine, that's as good as it gets in my field. These are some of the images that we made in the Jupiter system. These are all images of the same object. They're a moon of Jupiter called Io. It's a volcanic moon. You can see a volcano going off at the north pole of Io on the left. The color picture shows you the same thing, and that blue color for the plume is actual true color. By the way, Io is about the size of our Earth's moon, almost exactly. And then in the infrared picture in the lower right, you can see on the night side that there are volcanoes going off all over Io at any given time. These are the ones in 2007 when we flew by. And then we took a long 8-year journey at record speed and made records to cross the orbits of every planet. We've been the fastest planet to cross the orbit of Mars, the fastest spacecraft, cross the orbit of Mars, to cross the orbit of Jupiter, Saturn, Uranus, and Neptune, and of course, the first to Pluto. When we left Jupiter in 2007, we were looking at an 8-year flight to cross the 3 billion miles, and now we've done it all. During that period of time, we wrote all the software and tested it for the spacecraft scripts, the computer command scripts that fly the spacecraft through the Pluto system. We tested it on ground simulators, and then we actually put it up on the spacecraft, tricked the clocks out, told the spacecraft back in 2013 that it's 2015, and let it run through all of its paces, and it worked flawlessly. Now we're on approach. We're doing the real thing. We started in January, and of course the encounter will culminate in July. What are we doing? We're not just coming to talk to you. We're writing more computer scripts for the instructions that are still ahead for later this month and for next month and for the beginning of the downlink. We're navigating, taking pictures and sending them back to Earth almost every day to measure the position of Pluto against the stars that let our navigation team determine exactly where we are in space, exactly how far from Pluto, and when we have to fire the engines to make a course correction. The last time we did that was in March, and we made a very small course correction, just a few miles per hour, that put us right on target. And we were looking at maybe doing another 1 or 2 very small course corrections to make sure that we hit the exact aim point to get the very best science. In addition, as Joe told you, we're also looking for hazards, not just for data for the dust counter that Jamey's told you about, but actually we want to make sure that we don't hit anything that could damage the spacecraft. And at the speed that we're flying, more than 10 miles per second, even something the size of a rice pellet could break New Horizons. Think of it, how much energy would be in a rice pellet if it hit your windshield at 10 miles per second. So our cameras are also trained on the Pluto system to look for new moons, rings, other dust assemblages, and we prepare backup plans, actual entire fly through the system computer programs to go to alternate trajectories in case we find dangers along our path. And at the same time, we're analyzing the data that's coming back through Joe's pipelines every day. Well, we're on Pluto's doorstep, and we can't wait now to get the close-ups. I thought I'd show you a little bit of what we've already been obtaining. On the left is an image taken from that Laurie camera of Pluto. That's the bright headlight in the middle of the frame. Its moon Charon is lost in the glare, and those are stars in the field. But we can remove those stars and get rid of all that glare in the computer. And that's what you see in the middle frame. And once we processed it, we add some labels. And you can see if you look up there, over here on the right, those are Pluto's small moons, all 4 of them that we've now spotted on approach. They have the names Nix and Styx and Kerberos and Hydra. And we can now see all of them, and we're looking for even smaller moons that may orbit there. As Fran said, we don't know if we'll find 1 or 5 or 50, but we're now on the lookout. That's new data from New Horizons, and so is this. This is a movie of Pluto and Charon orbiting one another as seen from New Horizons from about 100 million miles out. You can just barely see the disk of Pluto, and if you look carefully in the lower right, we put an inset where you can see Pluto blown up to full resolution. Now, Pluto looks a little funky. You might think it's not round, but it actually is. That's just the image processing. And Pluto, like the planet Uranus, is lying on its side. So if you look at the 3 o'clock position in that inset, that continuously bright spot, that's actually the North Pole. And that's the northern polar cap that we think that we've discovered. And here you can see even better pictures made in April and in May that show even more details on Pluto's surface. And within a few more days, we're going to release pictures taken early this month in June, and I think you're going to be pretty impressed. I can't tell you what's in them just yet, but watch for them on the internet because they'll be out probably by Friday. Well, this is our Pluto-Palooza. This is our chance to tell you about what New Horizons is, about our excitement about going exploring, about making a little bit of history, and next we're going to answer your questions. So thank you very much.
I guess it would help if I hit the on button. Thank you to Alan and Joel and Fran and Joe to be part of our program tonight. And so we'll open it up to questions. And remember, we've got these marvelous bumper stickers that Alan provided us. So the first 5, and I think what I'd like to do is choose some of the younger people in the audience, and your mom or dad will get the bumper sticker, but doesn't mean you get to drive the car. But anyway, let's go with this young man in the blue shirt here.
If
So I think the question is, we're going past Pluto and continuing on. Will we be able to do anything with the Oort cloud?
That's a really good question. And the simple answer is no, because the Oort cloud is about 100 times farther from the sun than Pluto is. It took us 9 years to get to Pluto. You can do the math. That would be about 900 years. And the spacecraft doesn't have that much power to last that long. But we will go exploring further in the Kuiper Belt, going 3 or 4 times as far from the sun as we are now. Thank you for asking.
So by the way, if you would come down afterwards, I'll get you your bumper sticker. Let's go to this young lady in the black shirt here. You.
Fran?
How does Pluto maintain its atmosphere?
That's a very good question, because I said that it was losing its Pluto is losing its atmosphere. So the question is, how does it maintain it? And in fact, what's happening is it's evaporating from the surface. The ice on the surface is evaporating, just as we see here in Colorado every winter when we have a cold winter night, and in the morning the sun hits the ice and it evaporates. So it evaporates, and over time, and it takes quite some time, it escapes. And because Pluto's gravity is weaker, it escapes faster than, say, if it was the Earth inside there. And so it is escaping over time. And indeed, we think that as much as maybe 5 times the height of this room of ice could have been lost over the age of the moon. So it takes a long time to, that may seem like a lot of ice. It's tiny compared. Don't worry, Pluto's not going away. It's just slightly shrinking a little bit. So it's evaporation of frost that happens. But Pluto sometimes gets further away from the sun. Right now, it's pretty close to the sun. And what we want to think about when we fly by is the evidence that that atmosphere actually collapses and freezes back onto the surface when it's much further away. We're going to look and see if we can see that frost back on the surface. Good question.
Okay, all the way in the back, this young man, I can't see the color of your shirt, but you, yes. So if the sun has protons and neutrons, why doesn't it have electrons?
It does. I'm sorry. Maybe I misspoke or didn't say it very clearly. What's coming out in those big flares that are erupting, wasn't that a cool movie? Fantastic. Is mostly protons and electrons. So put those two together, you make a proton. Sorry, protons and electrons, you make a hydrogen atom, right? Proton and electron make a hydrogen atom. And they're equal numbers, so it's net neutrally charged, okay?
Okay, this young man, and yes, you. How do all of the 7 instruments work
Well, the
together?
short answer is they work really well. But each one works a little bit differently. Some of them use light and telescopes or other optics to make a picture at a focal plane. Others are spectrometers, so they actually break the light up into its individual wavelengths in the ultraviolet and the infrared parts of the spectrum. And that allows us to determine the surface composition and atmospheric composition. Yeah, that's those instruments. Then we have the dust counter that you heard a lot about that can hear the impacts on the spacecraft from these dust particles. They're on the bottom. Thank you. Let's take a look at SWAP and PEPSI. SWAP and PEPSI are measuring charged particles called plasmas in space to tell us about the composition of the material coming off of Pluto's atmosphere and escaping, as Fran described. And then the last instrument on board the spacecraft is our radio science. It uses that dish antenna and very sensitive receivers. And it can do 3 different kinds of things. It can determine the mass of Pluto and its moons from something called the Doppler effect. It can measure the temperatures on the surface. And by beaming radio waves from the Earth, perfectly timed to meet the spacecraft as it flies behind Pluto, we can measure the atmospheric refraction at exquisitely accurate levels. For those of you who are engineers and scientists, we measure it at about 1 part in 10 to the 13th. And we can determine the temperature and pressure profile all the way through the atmosphere with that instrument, the radio science instrument. Steve?
Okay, how about this young lady on the end over here? You.
Yeah, the question was how long can New Horizons fly?
Okay.
Because it doesn't have an infinite amount of everything. So everything's working, but we only have a certain amount of fuel. We probably have enough fuel for 100 years. But we do. But we don't have enough power for 100 years because that radioisotope generator, fueled by plutonium, has a half-life, and every year the spacecraft generates 3.5 watts less than the year before. So we started and we launched about 250 watts. Right now the spacecraft produces, and I'll tell you exactly, 201.6 watts right now. And in 10 years it'll be about 35 watts less, and eventually we'll get to a point where we can't run the radios and the main computer and at least one scientific instrument to send data back. And that's probably 30 years from now. Not quite, maybe 25 years from now. So the spacecraft can probably operate into the late 2030s. So by then, maybe you'll be in charge of New Horizons, because I hope that I'm operating at all by the 2030s.
Our final question of the evening right here. Yes?
What will happen to New Horizons when it runs out of power?
So what will happen to New Horizons when the power decays?
So there are two answers to that question. One is that the spacecraft will stop functioning and radioing to Earth and sending us data. But then what will happen? Because in space, where it's very cold, and the biggest things that hit the spacecraft are grains of sand that it takes a special instrument to detect, almost nothing happens. This spacecraft is going so fast, it's leaving the solar system and will escape into the galaxy. And you know, in a few billion years, the sun will become a red giant. And when it does, it will engulf the Earth and the inner planets, and the Earth will be gone. But New Horizons will survive. It will outlive the Earth itself. That's a great question to end on.
Yeah.